students, welcome to my YouTube channel. Today we are going to discuss one of the important derivation in our FEM subject, that is derive the element stiffness matrix of 1D bar element. In second module, this is very important for your university and examination. Okay, so for this we'll consider one prismatic bar that is fixed at one end. Okay, and we'll apply some force here, and here we have two nodes. One node is at fixed point and one node is here at the second point. Here the displacement will be u1 at node 1, u2 at node 2. Okay, here we have a prismatic bar fixed at one end, and this is node 1 and this is node 2. Displacement at node 1 is u1, displacement at 2 is u2, and the total length is L. Okay, here we are going to calculate the stiffness matrix. Okay, and here we'll be having F1 and this is F2. At node 1 this is F1 and at node 2 it is F2. Okay, at respective nodes. Now the total potential energy function, total potential energy function, we know the total potential energy function as per the minimum principle of minimum potential energy, that is pi is equal to, that is the sum of strain energy plus work potential. Okay, so here we have to calculate first strain energy for this prismatic bar. Strain energy for prismatic bar is given by half integration of here 0 to L, the total length is 0 to L, area A and Young's modulus E, and the displacement dou u by dou x with respect to x, that is square dx. Okay, and work potential, here we have two forces F1 and F2, and this is by the system, so we'll take it as negative F1 u1 F2 u2. Then we have to substitute this SC and WP in this equation. So pi is equal to 1 by 2 0 to L AE dou u by dou x whole square dx minus F1 u1 minus F2 u2. Okay, now for this bar element, here we have only two nodes. We have to assume a polynomial function, assume a polynomial function that is u is equal to a0 plus a1x. So here we have to apply the boundary conditions. Okay, here we have two boundaries 1 and 2. If at x is equal to 0, the total length is L, at the starting point the x will be 0. At x equal to 0, the displacement will be u1. At x equal to L, the displacement will be u2. First, at x is equal to 0, u is equal to u1. Now I will take it as equation number A. Equation A becomes u is equal to u1 a0 as it is plus a1 x is 0, anything into 0 will be 0, so a0 is equal to u1, that is a0 value. Similarly, at x is equal to L, u is equal to u2, the displacement at x is equal to L, here the displacement is u2. Okay, now equation A becomes u is u2 and a0 as it is, a1 as it is. This is L. Already we know the value of a0, that is u2 u1 plus a1 into L. Shift this u1 this side, that will be u2 minus u1 divided by, u2 minus u1 is equal to a1 into L. Then shift this L into this side. Here it is multiplication. After shifting this side, it will be division. So u2 minus u1 divided by L is equal to a1. So finally a1 is equal to u2 minus u1 divided by L. Okay, now I will substitute this a0 and a1 in this equation number A. So finally u is equal to, what is a0? That is u1 plus a1 is u2 minus u1 divided by L into x. See, this is the final u value. U is equal to u1 plus u2 minus u1 divided by L into x. Here we have, that is dou u by dou x. So differentiate, I will name it as B. Differentiate equation B with respect to x. Okay, so dou u by dou x, that is partial differentiation. Here we are doing with respect to x, so it will be 0. Here we have x becomes 1, so we will get u2 minus u1 by L. Okay, dou u by dou x, we got u2 minus u1 by L. So we have to substitute this dou u by dou x value in this equation. Okay, so I will write it here. Pi as it is, half as it is, 0 to L AE u2 minus u1 divided by 2, this is whole square, dx minus f1 u1 minus f2 u2. Here this is constant, I will take it as outside, 1 by 2 AE u2 minus u1 whole square divided by L square. This is L, this is L. Okay, as here we have L, so this is L into 0 to L dx minus f1 u1 minus f2 u2. Now we have to integrate dx. Here we have 1, the difference integration of 1 is x. AE by 2 u2 minus u1 whole square divided by L square, x limit is 0 to L minus f1 u1 minus f2 u2. So AE by 2 as it is. Here this is a minus b whole square, u2 square u1 square 2 u1 u2 divided by L square. After substituting limit, you will get L minus 0, that is L, minus f1 u1 minus f2 u2. This L and this square will cancel. Now remaining is AE by 2L, u2 square plus u1 square plus minus 2 u1 u2 minus f1 u1 minus f2 u2. Now as per the minimum potential energy theorem, we have to equate dou pi by this equation is equal to 0. As we have two nodes, first dou pi by dou u1 is equal to 0, then dou pi by dou u2 is equal to 0. I will name it as equation number 1. Now equation number 1, dou pi by dou u1. Here A by 2L as it is. See here we have u2 function, so we are doing differentiation with respect to u1, so it will be 0, and this will be 2 u1 minus, here we have 2 u1 u2, this will be minus 2 u2 and minus f1 as u1 becomes 1, and here we don't have that term, that will be 0 and that is equal to 0. So shift this f1 into this side, f1 is equal to AE by 2L 2 u1 minus 2 u2. 2 will cancel, so f1 is equal to AE by L u1 minus u2. Similarly, dou pi by dou u1 u2 ae by l, this is 2l constant. See here we have u2, so it will be 2u2, and here we don't have u2 term, this will be 0 and this will be minus 2u1, minus here we don't have that term, so this will be 0 and here we'll get minus f2. So f2 to 2 cancel, f2 is equal to ae by l. First I will write this minus u1 because here we have u1 minus u2. First I will write u1 to write in matrix form, plus u2. Okay, this is equation number C and this is D. Now we have to write the C and D into matrix format. Okay, f1 is equal to ae by l u1 minus u2, as f2 is equal to ae by l minus u1 plus u2. Okay, I will write this into matrix form. First I will write ae by l, ae by l, ae by l, that is common. I will take it outside. Here we have matrix and here we have some vector. Here also we have u1, u1, u2, u2. So here I will write u1, u2. See here with u1 the coefficient is 1. Here for u2 the coefficient is minus 1. Here the coefficient is minus 1. Here the coefficient is 1. And that is equal to, here we have f1, f2. After simplifying this, we'll get the same thing. Here this term we call it as the stiffness matrix, that is K, and this is global displacement vector and this is load vector. So where K is equal to ae by l 1 minus 1 minus 1 1. This is the elemental stiffness matrix for 1D bar element. Okay, thank you. In next video we will solve the example problems. Okay, thank you.